law of chemical combination is just trying to tell us one or two things about how elements combine in reactions. How elements combine. We are talking about chemical bonding. Chemical bonding is another thing. A compound can bond together, but there is a law that guides that bonding. So when you're talking about law of chemical combination, there are 4 laws. So I'll summarize the 4 laws in a simple explanation. You know, one thing about your JAMB is that having understanding is what matters. So for the 4 laws of chemical combination, the first law is called law of conservation of mass. And I think we talked about that yesterday. So law of conservation of mass is just stating that matter can, when we did the effective of the source, or where you get a compound or a molecule from. Almighty Jesari. Mando. So irrespective of the source, where you get a compound from, the ratio of the elements in the compound is always of a constant value, irrespective of the source. So every time you have a compound, the ratios of the atoms you have in that compound is always constant. What's the ratio of hydrogen to oxygen in water? Ratio 1. So if I get to US now and I ask them that, oh, what's up guys? In it. The water you guys drink here, what's the source and what is the ratio of the water, if you want to talk about it? So by the time I ask the class that what is the ratio, what would they tell me? Is there any difference between the water in Nigeria and the water in US? Yes. There is no difference. In chemistry, there is no difference. It is a constant composition. Do you get that? So this law is letting us to know that, okay, let me ask, between Nigerian water and US water, which one is better? You should like your country. Nigerian water is the best of water in the whole world. The first one, 64 ratio 16. The second one, 128 ratio 32. Then I keep increasing it just to test you. Now, at the end of the day, when you check, do you think anything is changing here? The ratio is constant. This is 1:4, Abi. This is still what? 1:4. So in that case now, your answer will be constant composition. It remains constant. Do you get it? So they might want to test your knowledge. We already know for constant composition, it must not change. It must be the same. But for multiple, one of them will remain constant, while the rest will keep changing. Do you get that? So if I give you a question and I say there's elements X and Y, one of them is 64, one is 16. Then later, the X became 128, but this is 16. Then later, 128 times 2, that's like 256. Then the next 16. When you check this, there's one I'm not changing. Which one am I not changing? Y, Abi. So in your option, which one will you pick as your answer? Multiple proportions. Do you get that? That's just the difference. For definite proportion, even if they give you several values, when you look at it, if those values maintain a particular constant, then they are just trying to test you. It can get, but most times they might not give you a question that will be that you have to that reason like that. But sometimes you too, you think like your examiner, especially when you have understanding of what you are doing. So it happens like that. So the last one.
So everything you say that is not here. Like, you said you have to recap.
I will have to recap. Which of the recapitulator? I said when two elements can form more than one compound, the ratio of the masses of the ratio of masses of one of the elements. But now I put it in the brackets. You know there are two elements, Abi. The ratio of one of them, which is what? The masses of one of the elements. One of the elements has different masses, Abi, compared to a constant or fixed mass of the other. So if you look at this now, between CO and CO2, they have ratio of masses, Abi. Which one is constant between the two of them? Copper, Abi. Which one is changing? Oxygen. So if you look at the two of them now, the ratio of one of them is different, but one of them is fixed. So when you have one of the masses fixed and one of the other mass changing, then you say you have, that means they can form multiple compounds. So they have different compounds that you can form if one of them is constant. We will solve questions, we will see other questions. Now, look at this. What I analyzed here. From what I analyzed here, I said, let's say I have two elements, X and Y, for example. If I have two elements, X and Y, law of multiple proportion is stating that you can form different compounds of X and Y. There are some elements that you see they are different compounds. You see NO, you see NO2, Abi, you see N2O, you see different things changing. So, if you can form different compounds, and look at this now, if I have this, let's say NCl, NCl2, NCl3, without saying anything, these three, which of the law do you think it will be between constant composition and multiple proportion? Because let's say I give you the value for N now, it will not change. But which one is changing there? Chlorine. But this is a compound, something chloride. This is also something chloride. But they can form multiple compounds. That's what that is just saying. That sometimes some elements, when they come together, they can form multiple compounds. Just like the way this one can form CO. CO is called carbon monoxide, Abi, and this one is called carbon dioxide. So you can form different, when you can form different compounds with the same elements, then you call it multiple proportions. Do you get that? But the only thing you should watch out for as a student is that if mass of one of the masses must be kept constant, while the other mass keeps changing. When we solve questions, you see. So to some extent, when two elements form more than one compound, how many compounds do we form here? Two. Abi, can you form more than one compound for water? Water is water, H2O, Abi. So it will remain constant everywhere. It's a different thing if you form H2O2, hydrogen peroxide, it's a different thing. Now, when two elements can form more than one compound, the ratio of the masses of one of the compound must differ compared to a constant or a fixed mass of the other elements. So you can change this that the ratio of the masses of one of the elements differs compared to a constant or fixed mass of the other elements. I've wrote that part, Abi. Of the other elements. You can leave this part. So, we are look at it now again, so that the definition will make sense. When two elements can form more than one compound, the ratio of the masses of one of the elements differs, Abi, compared to a constant or fixed mass of the other elements. Does that make sense now? So one of them is changing, Abi, while one remains constant. Is that making? So we call that law of multiple proportions. Then the last one, we call it law of reciprocal proportion. Here's that one. Law of reciprocal proportion. So law of reciprocal proportion state that when two elements combined with a third element, when two elements combine with a third element in a constant mass ratio, when two elements combine with a third element in a constant mass ratio, the ratio of the masses in which these two elements also combines, the ratio of the masses, it's a very long definition too. The ratio of the masses in which these two elements also combine is constant to each other. It's more of like reciprocating what they did. Listen to this. Let's say I have hydrogen. Hydrogen combines with oxygen. Let's calculate the mass. This is going to be 2:16, Abi. More like saying 1:8. Then hydrogen combined with sulfur. That's hydrogen sulfide. What is this going to be? 2:32. Now that's what? 1:16. Now, oxygen combined with hydrogen to give us 1:8 or 2:16. Sulfur combined with hydrogen to give 2:32. I said something. I said when two elements, the two elements I'm talking about now is sulfur and oxygen. When two elements combine with the third element, what's the third element now? Hydrogen. The ratio of the masses at which these elements combine with the third element is constant. When these two elements that combine now come together, the ratio in which they combine with this third element is going to be the ratio in which they will combine with each other. That part can be confusing. If I bring sulfur and oxygen together, I will form S. Normally it will be like SO, but SO is not a compound. But if you have SO, the ratio is going to be what? 32:16. Now, the only thing that will keep changing is probably if I now increase oxygen. So if I increase oxygen, it becomes what? SO2. What ratio will it be? 32:32. Now, how many oxygen do I have here? 1. What is that mass? 16. How many oxygen do I have here? So you can see that it's a multiple value of 16. So even if sulfur and oxygen comes together, they will combine at a constant value, which is that 32. What did sulfur use to combine with this? 32. What did oxygen use to combine with this? 16. So it's now saying that that same value they used to combine with this hydrogen is the same value they will use to combine with what? With each other. That's the simplicity. That's what it's saying. If oxygen combines with hydrogen and the ratio it's used to combine with hydrogen is 16, and sulfur combines with hydrogen and the ratio which sulfur combines with hydrogen is 32. When oxygen and sulfur combines, they will also combine in that 16 to 32. Let's read that statement again. Let's read the statement and see if what I have said, if it explains it. Oh yeah, one person should read it. When two elements combine, let's read as if we are reading Bible and explaining the church. What are the two elements combining with a common element now? Oxygen and sulfur. So when two elements combine with a third element, in a constant mass ratio. What's the mass ratio for this? It's always 2:16. You know the mass of, you know how I got this now? Mass of hydrogen is 2, mass of oxygen is 16. Mass of hydrogen here is 2, mass of sulfur is 32. Let's go on the other one. The ratio of the masses in which these two elements, which two elements am I talking about? Sulfur and oxygen. It's also what? Constant to each other. Do you get that? Compared to when they combine with these two, the ratio remains what? The same. So if I combine sulfur and oxygen, if you check the ratio, it will always be the same. Sulfur remains 32, oxygen remains 16. But even if I now have SO2, the only thing that just happened here is that the oxygen has now become 2, and when it becomes 2, it will maintain that ratio. Do you get that? It will still go 16, 16, 16, even if it becomes SO4. If it becomes SO4, what will it be? That means this will still be 32, but this will now be 16 times in 4 times, and what would that be? 64. Do you get that? So the ratio at which oxygen is always combining with sulfur is the same ratio that it's combined with hydrogen, which the basic ratio was 16. It now depends on how many oxygen is present, how many sulfur is present, and all of those things. This does not apply, but if you have this now, A2SO4, in what ratio would this be? 2:32:64. And why is it that this one is 64? Because there are 4 of it. Do you get the logic behind it? It's just like, just telling you that this thing is constant everywhere. That's what it's just trying to say. That if one element combine with hydrogen, it does not mean that if that element go and combine with another element, it will now be combined with different things. No, it's always the same in virtually all of the compounds. So it's a reciprocating thing. So what you do with this, we can do it to each other. That is what the word reciprocal comes from. It's one of the aspects that it's most times difficult to comprehend, but it's not difficult. Just know that when two elements combine with the third element, the ratio at which they combine with that third element is going to be constant, Abi, and the ratio at which those two elements also combine is also going to be what? Constant in relation to the other ones they combine with. Do you get that? That's what that part is saying. If you see question on it, you should know. Fe2O3 to Fe3O4. In this case now, Fe3O4. I'm trying to check the oxidation state of what you have here is a combined compound. You have FeO and Fe2O3. That's what you have. It's a combined compound. And we call this iron 2, iron 3 oxide. In this case now, this is iron 3. What has changed here is the oxidation state. This is plus 3, Abi, and this is plus 2. Now if you check this, will any of the mass change? Will any of the mass be constant? That's how you will know if it is multiple. If you check, both of them are going to change. Abi, they are going to change in value. So, in that case now, what you just have is a combination of different compounds. And this compound has a constant composition. This compound also has what? A constant composition. So if you see a question like this, it will be better to pick constant composition because they are changing. Do you get? Is that what? Yes. No mass is fixed here. Do you get that? If one of the masses is fixed, then you pick multiple proportion. But this is just a combination of two different compounds. So this one has a constant composition everywhere you go. What is the oxidation state of iron here? Plus 2. This one is minus 2. Abi, that's iron 2 oxide. This one is iron 3 oxide. So it's a different compound. But in order to maybe just twist it, is why they brought everything together. Normally, I could have written it like this: FeO dot Fe2O3. That's a compound, but with different oxidation states. And iron has ability to form that because it can form multiple oxidation bands. But how do you now know which one to pick if you see something like this? This is constant for its value. If you check this now, the mass for iron is what? That's 56. So this is going to be 56 ratio 16. Abi, this is going to be what? That's 1:1:2 ratio 48. Is there anyone that is constant here? You know, I told you that before you pick law of multiple, one of the elements must maintain a constant mass. Abi, so this value, if you like change it, it remains the same for this compound. For this one too, it remains the same for the compound. Anytime you want to form FeO, they must combine in the ratio of 56 to 16. Anytime you want to form this one, they must combine the ratio of this to this. Do you understand my explanation now? So please, that's what you just check for. So let's see questions. Oh yeah, let's see questions on that. Have you solved some questions on multiple proportions before? Oh yeah, let's see. From your past question, chapter 2. Okay, yeah, let's see, chapter 2. So I will ask you a question and you tell me the answer. If you can tell me the answer, then. So the first law is called law of conservation of mass. The mass remains constant on left side and the right hand side. The second one is law of definite proportion. That means irrespective of where you get the compound from, the proportion is always constant. Then the next one is law of multiple proportions. You can have different compounds for two different elements, keeping one of the elements mass constant. Then the third one, reciprocal, is now saying that if two elements can combine with one element at a particular mass ratio, It is the same ratio at which they combine with that element that they will also combine with each other. So they reciprocate it. Oh yeah, let me see. Oh yeah, everybody, question 8. Question 1. That's chapter 5. Can you see question 1? Eh? Oh yeah, let's check number 1. Then we also check number 2. Chapter 2, yes, particulate nature of matter, chemical formula and equations of chemical combination. You don't have it. No, I said page. Oh, sorry. I thought I said page 5. Page 5, chapter 2. Have you seen it? Eh? An element X forms the following compound with chlorine. There's an element X. We don't know what the element is. It forms different compounds with chlorine. What law does it illustrate? A. Multiple proportion, chemical proportion, simple proportion, conservation, definite proportion. Eh? Why did you say multiple? Because X is not changing. X is kept constant. And chlorine is the one changing. That means they can form multiple compounds in different proportion. That's the name. Let's just check number 2, but number 2, I don't know what. An experiment test of the law of conservation of mass is illustrated. It's just talking about maybe a reaction. The flask is weighed before and after the reaction between solutions X and Y. That means, for law of conservation of mass, what does that mean? They said they weigh it before and they weigh it after. For law of conservation of mass, what do you expect? The mass should be the same for the before and for the after. So let's go on to see what they are now asking. Which of the following pairs of solution would be unsuitable for the experiment? Which of them would be unsuitable for the experiment? A. HCl plus silver nitrate. HCl plus silver nitrate. Let me even call it. There's a reaction in which an acid can displace another acid from its salt. HNO3. From this now we can have your HNO3 and HCl and HCl. So an acid can displace a weaker acid from its salt. Let's check the other options. Barium chloride will dilute sulfuric acid. That's H2SO4 and BaCl2. In that case now, we usually use barium chloride to precipitate, so it can now be SO4 plus HCl. H2SO4 is stronger. So the next one, HCl plus sodium hydroxide. So what would that give us? I'm just writing the reactions out so I can think about what they really want us to know here. If you check about it, it can just be one of them that is used to HCl plus NaOH, right? So that will give us NaCl plus H2O plus nothing. Okay, that's salt and water. That's an acid and base. Then the last one, HCl. Oh, they are still D and E. Those people that used to write JAMB in all those 1978s, how much it more? That's HCl and lead nitrate. That's PbNO3. So just like the first one. HNO3 plus PbCl2. Finally, HCl plus sodium carbonate, HCl plus Na2CO3. So that will give us NaCl plus H2O plus CO2. So the question here is saying that which of the following pairs of solution will be unsuitable for the experiment? Naturally looking at it, which one do you think should be unsuitable for the experiment? Why? Why did you say the last one? Because the CO2 will be escaping. The CO2 is a gas, Abi, and you know you want to collect it and weigh it again. You want to prove law of conservation of mass. So you now weigh before and you weigh after. But you know, if during this one you are producing CO2 and CO2 is a gas, what will happen to the CO2? It will start escaping, especially if it is an open system. And from what they have shown here, it looks more like an open system. So CO2 will escape. I think it's even carried out in a test tube. Abi? Then the test, X is in the test tube, then Y is in the solution. Okay, maybe they are just putting it inside. So at the end of the day, the one that will be unsuitable is the one that is producing gas, because it might not be easy to weigh the gas compared to others. This one insoluble, this one insoluble. This is a liquid, an aqueous solution. This is an aqueous. This is solid, this is liquid, this is aqueous because it will dissolve in water. This is aqueous, this is solid, insoluble. This is aqueous, liquid, then gas. So you see that the one that has gas is actually the one that might be unsuitable. But if they want to measure the mass, it's not that they cannot measure it. They are just saying that which one would be at least unsuitable for the experiment. So do we understand that? The only way you might not understand is maybe you are just wondering that how did we know these reactions? We will do acid, base, and salts. All of them came from acid, base, and salts. Maybe that will be our next topic. Are we there? So which one is next? Let's look at question 8. In an experiment, are you following? 5 grams of a metal gave 10.59 grams of its chloride. Of its chloride. In another experiment, 1.50 grams of the same metal combined with 1.68 grams of chlorine. What does the above data illustrate? So what do you think they are trying to say here? What you are going to do is check the ratio. Abi? The first one, 10.59 to 5. Try to divide 10.59 to 5. What do you have? Eh? 2.118. So you have to do 1.68 divided by 1.5. The values are different. Is it the same or different? They said, please listen again. In an experiment, 5 grams of a metal gave 10.59 of its chloride. We have removed that of its chlorine from PFS. You know that he gave 10.59 of his chloride. That means the metal reacted with chlorine to give the metal chloride. So you can say 10.59 minus 5. That would be what? 5.59. Abi? That would be that of the chlorine. So you can now check. I'll write it on the board what I'm saying in case you don't understand. But I've not even gotten it yet. That's right. So 5.59 divided by 5. 5.59 divided by 5. So 1.68 divided by 1.5. But that first one you did, so you go 1.118 now. When you did 10.59 divided by 5. Okay, you got 2 points. In that sense now, can we say that it's an approximated value? 1.1 to 1.12. Do you understand what I'm saying? Let's check it out. Let me to roll it. Please, you don't start. What did they say here? Oh yeah, look up. Let's look at it together. So you will not pick the answer. They said there is a metal in an experiment, and the mass of this metal is, this is experiment 1, is 5 points. Abi? They now said this metal gave its chloride. That means it must have reacted with chlorine, Abi, before it will give its chloride. I don't know the formula for the chloride, but let's say that's the chloride. When it reacts with chlorine. But let's just say whatever it is. This is the metal chloride now. And what is the value? 10.59 grams. Funniest thing is that might be divide 5.50 by 5. 5.50 by 5. Okay. Now look at what we have here. What do you think is happening? From law of conservation of mass, the total mass on the left must be equal to total mass on the right. Abi? So now, if 5 grams reacted with chlorine to give 10.5 grams of magnesium metal chloride, what do you think is the mass of this guy? 5.59. Do you understand that? That's 5.59 grams. That's the mass of the chlorine. So now, in experiment 2, they now say that, what did they say? 1.50 grams of the same metal combined with 1.68 of chlorine. Abi, if they now ask you that what is the mass of the chloride form, what would that be? You will add this, Abi. That would be like 3.18 grams. You don't need this, but I'm just saying. Do you understand what we did in experiment 1 and experiment 2? We want to prove a law. So the law we want to prove, we want to know. You can see now that they didn't tell us the formula. So we cannot assume maybe it is multiple or maybe it is constant. Abi? So we can only prove it from the experiment. So now when we check, what are we going to have? The ratio of this to this and the ratio of this to this. If you check the ratio of this to this and the ratio of this to this, if it is the same, then you say it is definite proportion. But if you check it, even from what we are seeing here, it's showing that it cannot become multiple proportion because this one changed, Abi, this one also changed. One has to be a constant to be multiple. Do you get my point? So now, at the end of the day, let's check the ratio. This one will be 5.59 over 5. That's the ratio. And this will give us 118, which is approximately 1.12. Check it. Let's check the ratio for these two. So this will be 1.68 divided by 1.50. What would that give us? So that's 1.12. So you see that their ratio is constant here. Their ratio is also constant here. Show you, it's more like just telling you that water, this is 2:16. I can decide to say that this is, depending on the amount I have, I can say this is still 4:32. Abi, I can decide to still say This is 8:64. Abi, I'm still saying the same thing. So if I say 16/2, that will give me 8. If I say 32/4, that will give me what? 8. If I say 64/8, that will give me what? 8. So it's constant. Please, do you understand this? So our answer is what? Law of constant composition. Thank you. So the next one is what? 21. You should be able to solve those ones there from all the things we have done before. But if there's anyone you can't solve, then we'll look at it. Oh yeah, look at it. 2.25 grams of a sample of an oxide of copper on reduction gave 2 grams of copper. 2.50 grams of another oxide of copper on reduction also gave 2.0. Now that you have even seen that, what do you think that is talking about? What? Did you say constant? What's the answer? Verify, but from what is here, you would have seen that it's actually multiple. Abi? Are you following? So they said that 2.25 grams of a sample of an oxide of copper on reduction gave 2 grams of copper. What is the mass of the oxygen in that first experiment? That would be 0.25 grams. Abi? So that means the ratio of the mass of oxygen to that of copper is 0.25 to 2. And in the second experiment, the ratio of oxygen, I think, okay.
Can we check?
So, okay.
Can we check?
So,
2.25 grams of a sample of an oxide. So there's an oxide of copper. I don't know what the oxide is, but they said that the total mass here is 2.25 grams. Abi?
They now said that on reduction, it gave 2.0 grams of copper. That means that this will give copper plus oxygen when you remove oxygen. So now the copper is 2.0 grams. That means the oxygen will be what? 0.25 grams. Then in another oxide of copper, in this case now, I'm just writing O. I don't know what it is. This one is 2.50. What's the increase in mass? But something did not change. They said that this one also gave 2.0 grams of copper and whatever 0.50 of oxygen. Oh yeah, let's check the ratio in case that's their question they ask you. For the first one, that is, let's just say this one did not change. I don't want to divide it. Let's say this is 1. 2 divided by 0.25 will give what? 8. So this is 8:1. Abi? What would this one be? 4, Abi? This is what? 4:. Is that correct? So, if you look at what we have here, in terms of the ratio, although is this one that is actually changing in mass, Abi, but we kept this one constant. We are just trying to get the ratio at which they are combining. So this one now, as it maintains is 1, this one has gone down to 4. It's obvious from here that one of them maintains its mass, Abi, and one changes. It's the ratio at which they combine. That's what we are doing here. But however you do it, one will be constant and one will keep changing. Do you get it? And if one keeps changing and one remains constant, that means that is what? Law of multiple proportions. You have to be sure of your answer. So they can make it look like this. But the moment you shall see that. And another thing is be careful. Always do this thing I'm doing. You can do it now and get the same ratio. And you saw that one was constant. You now chose the answer. You did not check first. If I had done this, and it eventually gives me 8:1, and I do it again, it still gives me 8:1, your answer will be constant composition. Do you get that? So don't just look at the mass alone, check the ratios too. So what if you look at the masses now, you see that it looks as if oxygen is the one changing, which is true. But if you look at the ratio, oxygen is the one that is remaining constant, while the copper keeps changing. But if not for we don't know the formula, we would have said which one is actually changing. But we are just comparing the masses, so it's not really a big deal. We saw that one changed and one remains constant, and we don't expect the. But this could have changed in a proportion that we go in line with this. This one might have increased to 10, and this one will also increase to maybe around 5 or thereabouts, and you will still get the same ratio. So it's not that. Please, do we understand this? As long as one is constant and one keeps changing, then you say it is multiple proportion. Is that all? Can you check 25? What's the answer? Look at this one now. You never can tell. Don't just say it is constant composition until you check. Is that taken? So you check. You have two separate experiments, 0.36 gram and 0.79 gram of chlorine combined with a meta X to give Y and Z. On analysis, show that Y and Z contain this and this of X. What does the data represent? So you have to verify. We have to do that and tell me what your answer is. Oftentimes they don't ask questions on reciprocal, but just know it. They might ask you during your own time. Which one is number 6? Which one are you saying? Number 25, Abi. What's the answer? I'm sure that some of you up till now, either soft copy or hard copy, you don't have past questions up till now. Up till now, you don't have past questions. Well done. Odogu. Continue. You have 2 months left. You can still redeem yourself. What's the answer? Do you all agree that the answer is constant composition? So if you don't have past question. So number 6, someone said that he does not understand number 6. In the reaction of oxygen with hydrogen to produce water, which of the following statements is true? When hydrogen, let me give you all the different terms you can hear. Hydrogen combining with so you have hydrogen combining with oxygen to give water. That's the balanced equation. I still want to teach you Gay-Lussac's law. That's the balanced equation. Now, from this balanced equation, please listen. You can have different interpretations. You can say, this is how you interpret in chemistry. 1, 2 moles of hydrogen, our chemists can teach us, of hydrogen reacts with 1 mole. So plus means reacts for the learner of science. Okay, but really actual bad. We need 2 moles of hydrogen. 2 moles of hydrogen. Plus means reacts in science. So in commercial it means addition. But in science chemistry it means react. react with 1 mole of oxygen to give, this one means to give 2 moles of water. To give 2 moles of water. In another case, you can say that 2 volumes of hydrogen react with 1 volume of oxygen to give 2 volumes of water. If they are all gases, you can say that 2 volumes of hydrogen react with 1 volume of oxygen to give 2 volumes of water. That's another way. And you can say that 4 grams of hydrogen react with 32 grams of oxygen to give 36 grams of water. As simple as that. You can say 4 grams of hydrogen, you know how I got that 4 grams. 4 grams of hydrogen react with 32 grams of oxygen to give 36 grams of water. So those are the different interpretations. So now option A says that 1 atom of hydrogen reacts with 2 atoms of oxygen to give 1 molecule of water. Is that correct? No. The 2 atoms of hydrogen react with 2 atoms of oxygen to give 2 molecules of water. Is that correct? Atoms are different too. How many atoms react here? These are 4 atoms. Do you get that? The total number of hydrogen you have here is 4. Abi? This 2 is just telling us that I need H2. Atuni H2. So I don't have to start writing. How many do I have all together? That's where we started the atomic structure from. That's why I said if you don't understand the difference between atom, elements, molecules, and all of those things, you can have some bit of problems in stoichiometry. So there are 4 atoms here. 4 atoms of hydrogen react with 2 atoms of oxygen to give 2 molecules of water. Shoye. The next one. Which option is next? C. 1 molecule of oxygen, that's still correct. Reacts with 1 molecule of hydrogen, is that correct? No. It's reacted with 2 molecules of hydrogen. Then D. 1 molecule of hydrogen reacts with 2 molecules of, that is also wrong. Abi. Then E. 1 molecule of oxygen reacts with 2 molecules of hydrogen to give what? 2 molecules of water. That is correct. Is that taking? Those are the different interpretations you can have. Are we through with the question 30? What's the answer? Conservation of mass. Question 32. I think that question is not complete. They just said 2.8. It should be like that 21 we solved. But they said 2.85 grams of an oxide of copper give 2.52 grams of copper on reduction. They are both illustrate the law, so it's not complete. It's not an evidence to prove. Can you answer 38? Want to run away. You wanna run away. Don't run away from problems. Don't want to see. Olayanju Josephine, Omobolaji, love, remix, chemistry, love. So, I've answered your question. So let's look at the Lusaac law. Don't worry. I have a couple of things to do too. Okay. Most times, Tabawa class, we shape our knowledge and I can believe as important more than we carry ourselves. That's the problem. We can't be more important. and we count ourselves. If I do not come today now, it does not cost me anything. Your class is Monday to Friday, so a lot of people did not come now. So, because everybody don't man make it. That's why you should not compare yourself to anybody. And don't do what some people will do. Some people will come on Monday now, they'll just be joking with you, be playing with you. Look at class night, might not see them. That's a sign that you know that you're really serious. So except that you have a genuine reason for not coming. But I have a lot of reasons not to come. I have a lot of reasons. Reasons that I'm going to face some of the consequences. I have a lot. But sometimes we put you first. Because you're a princess. She like a boy. I mean a princess. She is a boy. He's a prince. So, Gay-Lussac law will be true. Gay-Lussac law of combining volumes. Gay-Lussac law of combining volumes states that when gases combine, they do so in volumes which bear simple ratios to one another. Gay-Lussac law states that when gases combine, they do so in volumes. They do so in volumes which bear simple ratio to one another. Which bear simple ratio to one another. So, first thing you want to make sure you look at is that when you are applying the Lussac law, it's only applied to gases. That's why the law states that when gases combine, they do so in volumes. So it's focusing on gases. And from what we have here, this is 2 ratio 1, ratio 2. So they can tell you sparking. Where is that sparking question? So they can tell you that hydrogen gas is completely sparked. That's where she got the title sparking from. Hydrogen gas is completely sparked with oxygen. If 100 cm cube of hydrogen was sparked with oxygen, what is the volume of steam obtained? Or the volume of the residual gases? Let me just give you this. If this is 10 cm cube, we all know what this will be. Abi, this will be 5 cm cube. This will be 10 cm cube, right? So that is the thing. Now, they can now ask you that when they give you a question that you should calculate volume of residual gases. When you hear the word volume of residual gases, it's saying that you should calculate all the volumes you have left. Both the volume for the reactants that you have left plus the volume of the products reactants left. plus the volume of the products. That is called volumes of the residual gases. Questions can come in different forms. That's why life is hard. So, another thing is that you can have some conditions. That anytime you hear those conditions, know that you have to remove some things from your calculations. One, if you're told that the reaction was carried out at room temperature, you have to be careful. At room temperature means you have to get rid of water in your calculations. Remove water. At room temperature, water will be what? Liquid. Abi. But when do you have water to be steam, to be gas? Okay, in case you don't know, water will only be a gas at 100 degrees Celsius. And what did Gay-Lussac state? Gay-Lussac said that this law of saying 10 cm3, 5 cm3, 10 cm3 only applies to gases. So if a question now says at room temperature is below 100. Normally, in a normal condition, it should be around 25 degrees C. But everything is always thought these days. So it should be 25 degrees C, that's room temperature. So at room temperature, this thing will not be vapor, it will not be gas, it will be water. So when you do all your calculations and stories, you must not add volume of steam to it, because it's no longer steam, it is now water. So if you read your question, and your question says that this experiment was carried out at room temperature, whatever volume you get for this guy, don't add it to your final answer. Do you understand my story? Second condition. You don't understand the story. Let me help your life. Drill. 40 cm3 of hydrogen gas was packed. Don't give up, my sister, is not over. When you give up, then it's over. 40 cm3 of hydrogen gas was packed with 30 cm3 of oxygen. 30 cm3 of oxygen at 25 degrees Celsius. At 25 degrees Celsius. Determine the volume of the residual gases. Determine the volume of the residual gases. We need a marker. A marker is needed at the front. We need a marker. Where's the person? If there's no marker, you can supply an ink. Nobody's answering. That means we should continue with our marker. We need a marker. A marker at the front. If I sing the song, I'm gonna sell. And even be on the billboard. You don't believe me, you don't have to. But when I make it, don't say, I know you, I know you. Even if I'm not selling, at least we carry on back. Number one fan. So, this is a question now. You have to always check the ratios to know what your answer will be. This is 2:1. The fact from what Samuel taught you on limiting and excess reagents, it does not mean that when you have something, you have to finish it. Does not mean. It does not mean that because you have too much water in your house, you have to use everything. You can only pick a part you need for your reaction. Why are you smiling? You don't have water at all. I said it does not mean if you have too much water, you're not smiling. It does not mean it.
So from what we have here,
H2 plus O2 to give 2H2O. Now, you were supplied 40 cm cube of hydrogen, Abi. You are given 30 cm cube of oxygen. So, during reaction, from what you have, what is the volume of hydrogen that should actually react with volume of oxygen?
From what you can
see here, it is 2:1. If this guy is 40, what should this guy be?
20.
But what do you have? 30. If this guy is 30, what should this guy be?
60.
60. So if I ask you, which one is limited out of the two of them? Which one is in excess? Hydrogen is limited. Because if oxygen says is given 30, hydrogen must give 60 before the reaction will complete. So now, but oxygen now has 30 and hydrogen has 40. So what do? Hydrogen will say, oh, let me give 40. If I give 40, all you just have to give is 20. Then you can keep your 10. See, I look for more of myself. So during reaction, what you are going to have is that you are going to have 40 cm cube of hydrogen. It will react with 20, just 20 cm cube of oxygen. And what amount of H2O will be produced? 40 cm cube of H2O will be liberated. So at the end of the reaction, you are going to have nothing left for hydrogen. That's why the reaction stops, because you have used hydrogen completely. Then what will you have left for oxygen? 10 cm cube. That can still react more if you have more hydrogen. Then you would have produced 40 cm cube of water. But now, they now say you should calculate volume of residual gases. If your question had said at boiling points or at 100 degrees C, then your answer will be 10 plus 40. But now that your question says at 25 degrees C, that statement alone means that this guy is no longer steam, it is water. At 25 degrees C, this is going to be water. No. Why this is going to be a gas and this is going to be a gas. So if I now say volume of residual gases, I'm not focusing on water. I'm focusing on what gas is left. So what is the volume of gas left?
just 10 cm.
So my answer will be 10 cm cube. Do you get that? So that's that statement 1. That's condition 1. Condition 2. Condition 2. If caustic alkaline, either caustic soda or caustic potash, alkaline pyrogallo. Let me do that first. If caustic alkaline, remove CO2. If alkaline pyrogallo, alkaline pyrogalol, heated copper, or burning phosphorus. So when you hear a statement like this, remove oxygen. So if this question had said this, that
at the end of the
reaction, no, this mixture was not passed through any of these things. If it's passed through
any of these three, that means the final answer is 0. That means it will be
0. There will be nothing left for oxygen. These guys are used to dry oxygen. Is that taken? But if you have a reaction that involves CO2 and it says sodium hydroxide or potassium hydroxide is used, that means you remove CO2. Then if the question says that if calcium chloride is used,
so if they use,
if calcium chloride is used, then remove steam. Remove steam. That's another condition.
so anytime you hear any of
These conditions, you have to be careful to know what to pick. So, without wasting much time, please, as much as possible, we have been slow with our classes. We are not rushing, except that
still have a lot to do.
we have a lot to do. So by next week, I'll do my best again. What's the time? So that your dinner can easily go for your dinner. So have we gotten our answer? Oh yeah, let's look for questions now. Questions. Your past question. I can give you questions now. Just one question, I'll cover everything. But let's solve from your part. Oh yeah. One or two examples, and I move to current electricity. We can pass it. Just say the number. Is it from the past question? Okay, you have a question. Let's see. Please send it to me. Okay. Right. 10 cm cube of carbon monoxide. 10 cm cube of carbon monoxide, CO, is mixed and sparked. With sparked is SPARKED torí ti lè kọ sí bẹ́yẹn. Bóyá kí ló sparked. I'm teaching you pronunciations in English. There are some words that it's with ED, and it's going to be pronounced the past sentence. 10 cm cube of carbon monoxide is mixed and sparked with 100 cm cube of air. 100 cm cube of air containing 21% oxygen. I think that was the question someone gave me yesterday. Containing 21% oxygen. If all the volumes measured at STP, or the secondary school teacher, no, it's my body. If all the volumes measured at STP and the volume of the resulting solution is passed, if all the volumes measured at STP and the volume of the resulting solution is passed through alkaline pyrogalol, And the volume of the resulting solution is fast through alkaline pyrogallo. And caustic soda. And the volume of the resulting solution is fast through alkaline pyrogallo and caustic soda. Caustic soda. What is the volume of mixture left? What is the volume of mixture left? That is like saying volume of residual gases. So, first is to balance the equation. You have carbon monoxide, you spark it with air. What are you trying to pick in the air? Oxygen. Abi? So now, just continue what you are doing. So you took carbon monoxide, you sparked it with air, but what is reacting in the air is oxygen. Then that gives us CO2. But if you balance the equation, you're gonna have 2N2, right? That is 2:1:2. You already know what it is. Now, what's the volume of CO given in your question? Eh? So the volume you are given is 10 cm³. What's the volume of air given? 100 cm³. There's something that says 21% for sure. So out of the 100, you have 21% oxygen. Abi? You can determine the volume of oxygen, but let's hold on so that some of you don't get confused. I'll now come back to tell you what I want to tell you. So, during reaction, what are you going to have? This is 2:1, Abi. So normally this is supposed to be 10 cm³, and this is going to be 5 cm³, Abi. Then what will you produce? 10 cm³. Are you following? That means that at the end of the reaction, you will have nothing left for this, right? What will you have left for this? And what will you have left for this? But the question now says something. Normally, let's forget all the conditions. That means that the total volume of all gases left is going to be, that's the volume of air. You don't know, oxygen is part of the air, whatever is part of the air, plus the volume of CO2, Abi, and that's going to be 95 plus 10. That's 105 cm³. That's not the answer. I'm just saying that, forgetting all condition, this is the total volume of the gas you have left. Let's now follow the conditions. Number one condition is that you have 21% oxygen. Let's determine the volume of oxygen. Go first. Volume of oxygen, percentage of oxygen is going to be volume of oxygen over volume of air, Abi, times 100, right? Are you following? And percentage of oxygen is 21 equals the volume of oxygen over 100 times 100. Do you agree? 100 and 100 is 79. VO2, volume of oxygen is going to be 21 cm³. So out of 21 cm³, how many did you use? 5. So what is the volume of oxygen left? 16 cm³. I hope you are following. So the volume of oxygen that is left is equal to 21 minus 5, and that's 16 cm³. We have not solved the problem. The question has said something that's, what's it? The volume measure that testicles pass through. So they now pass it through alkaline pyrogallo. Passing it through alkaline pyrogallo. You know now, if you look at it, this is the total volume length of air, Abi. But that means that if I say volume of air is 95 cm3, and you have 16 cm3 of oxygen here. So if you remove that of oxygen, volume of air without oxygen is going to be 95 minus 16. Do you agree? And that's going to be 79 cm. So we now passing through pyrogallo. Passing through pyrogallo, what did you remove? It will remove oxygen. So meaning that the volume of oxygen here will be dried. Then what else did we pass it through? Caustic soda. What will caustic soda remove? CO2. So let me now show you where the problem is. The total volume of residual gases normally is going to be volume of air without oxygen plus volume of oxygen left, Abi, plus volume of CO2 produced. And that is what we did here. Volume of air without oxygen is what? 79 plus volume of oxygen left 16 plus volume of CO2 produced, and that gave us what? 105. Abi, do you understand this and this? I'm trying to make it understandable. That's why I'm even breaking it down. Which parts do you not understand? Let me go back again. Let me rub this part. Should I rub it? Let me rub this part. Maybe that's what is confusing you. So yeah, look at it. Do you understand to this level? You know, I'm using air. This 100 cm3 is not only for oxygen. It contains nitrogen and the noble gases, CO2 and so on. So now, but our focus is that in this place, CO will only react with oxygen, I mean, in the air. And we don't know the volume, so we are less concerned. Normally, you are supposed to start with this if you want to be very wise. Because what if after calculating percentage, you got 3? If you get 3, then that means this will be 3, this will be 6, then this will still remain 4. I don't know if you understand that part. Your question, your solution is actually supposed to start from here. But I just decided to move on first, that we'll discover along the way. Now, if you understood this, they now told us that 21% of oxygen is what we have in this 100. And percentage of oxygen is going to be volume of oxygen over volume of air times 100. Abi? So again, volume of oxygen is going to be 21 cm3. Now, if you look at it, we have only used 5 out of 21 cm3. Do you understand that? So what do we have left? 16. Volume of oxygen left is 16. But if we say here, we have only used 5 out of the 100 of air. So volume of air left is 95. But what is the volume of oxygen left? 16. So out of the volume of air that is left, if I remove oxygen, that means in the volume of air now without oxygen is going to be 79. Do you agree? Because the volume of air left in total is 95. But out of that volume left, I have 16 cm3 of oxygen. You know how I got that 16. So I have 16 cm. That means that the volume of air I have left without oxygen is 79. With oxygen is 95. Do you get that? Now that we know that, that means that the volume of residual gases is going to be volume of air without oxygen, volume of oxygen, and volume of CO2 produced. And that in total will be 79 plus 60 plus this will be 105. Abi? The question now said something. It said we pass it through pyrogallon. And pyrogallon will help you to dry oxygen. That means we first remove that one. The next thing, we pass it through caustic soda. That will help you to remove. That's why I had to break it down so that you understand where I'm removing from. Then it said after you have removed CO2 and oxygen, then calculate the volume that is left. Then, if not because we were not provided an information, I would have also said it that even volume of the air contains CO2. And the CO2 could have also been dried by the caustic soda. But we're not given any information concerning that, so we can neglect it. You might not get what I'm saying. So at the end of the day, final answer is going to be what? 79. So that will be the answer. Give me the notes. Notes and so
Yes.
Okay. Oh, it's like you are the one that gets. When I saw that solution, yes. They won't be produced. We were not told anything about the one present in us. So that's why we neglected it. You can have air and probably CO2 is not present. We were not told. If we had been told, we could have worked with that too. Then we remove that. We remove it from here. We also remove the one produced because that's what this guy will do. It will dry them off. So John is not totally complete, but that's the answer. If you want to be perfect with it, then you know that the question is not complete. But answer. Please, do you understand what I did here now? And these are the ways questions can come. Just to, well, it's not always that. There are different ways in which question comes, so keep solving. Keep solving. So, that's all about stoichiometry and calculations. Ephraim. So, that's all. Is there any question left in stoichiometry? He has taught you the dilution theory, C1 V1 equals C2 V2. So, what's our next topic now? Respiratory. In chemistry. I think we should move to oxidation. There are some topics that even if I'm not around, I have people that can do them with you always. So we should move to oxidation and reduction in the next class. Then talk about electrolysis. All those acids are salts, nuclear chemistry, water. We can still do them. So, but let's talk about oxidation, reduction, and if next week is enough for me to cover everything, so by Monday we'll try to cover oxidation and reduction, Tuesday, Wednesday for electrolysis, then Thursday for probably thermochemistry, then Friday, depending, then Saturday for chemical kinetics, and we end it. The next week you do your water, acids and salts for you. So, for physics, keep solving, no. Now you are supposed to just be solving questions when you meet your friends, ask them questions. Are we meeting tomorrow? So, we are meeting once before tomorrow. You are the church now. It's meeting to 1 to 2. Tomorrow is not first Sunday. Blessed. It's alright. It's alright. Can we have overnight class today? We don't have that. If I want to have overnight class, it can only be probably with the students. Parents in one house, you know, ọmọ wọn rìn kiri, ọmọ tó kúrò létọ̀ ọmọ bí tó lọ, tá ló wá overnight class, wọ́n kò bá yà. So should we do physics? Or you are tired? Everybody is fasting. But you are busy. What's the time? 9:156. Even me, I've never had time to charge my time. The last time I charged this thing like this, I can't remember. Okay. Kilo so. Okay, the third group. So, current electricity. We can do it in 3 now. Yeah, okay.